All right. Thanks, everybody, for coming. I'm very excited today. It sounds weird to me. Is it all right? Okay. I'm very excited today to introduce Levi Hargrove from Shirley Ryan AbilityLabs. Levi got his bachelor's, master's, and PhD all at the University of New Brunswick in electrical engineering, working with Kevin Engelhardt there before coming to the US at what was the Rehab Institute of Chicago, now is Shirley Ryan AbilityLabs, where he is the overall director now of the Center for Bionic Medicine and scientific chair of that line of research there. He's also an associate professor at Northwestern University in both physical medicine and rehabilitation, as well as biomedical engineering. And Levi has been running a program now for a number of years, really focused on neural signal processing and control of bionic limbs, both upper and lower limb. His teams now has been doing a lot more hardware development. As you'll see on this front slide these days, especially, I think they've successfully sold their upper limb technology, and they've been developing legs now for quite a few years and have some of the best leg technology now that's out there. And another key area that the center under Levi's direction has been moving is in invasive intramuscular EMG recordings and neural interfaces, both surface and invasive, for prosthetic users. Levi directs a group of 3 different labs within the Center of Bionic Medicine on various aspects of amputee prosthetic health. And this is a large portfolio. He's published over 200 papers in it. And I think one thing that sticks out to me and to others is Levi's mentorship of really top people in the field. He's now placed a lot of different professors who at top R1 universities in the general field of wearable robotics that have moved on to be quite successful from his guidance. That includes myself and quite a few others now that I think we all know in the field. Lastly, I think this is one very cool thing about Levi is that in his day job is really directing the Center for Bionic Medicine at Shirley Ryan. But at night, he is working basically on a startup company called Coapt, which he co-founded about 10 years ago to commercialize pattern recognition technology for upper limb EMG-based control, which is something that people have been saying in papers. This technology is so close to being ready for a very long time, and they finally did it, and really has been the company to do kind of machine learning-based upper limb prosthetic control, which has been really cool. And he still directs that as the scientific leader of that company as basically a second full-time job. And with that, let's thank Levi for coming here today, and I'm very excited to hear his talk.
Well, thank you, Aaron. I appreciate that. Is the mic coming through okay? Is it fine? Yeah. Of all of those accolades, the thing that I am most proud of is the talent development that's came through the Shirley Ryan Northwestern ecosystem. So if we had to brag about anything, it would be the people, although we think the hardware is decent too. Disclosures. So I have a financial interest in these companies: Coapt, Liberating Technologies, Interface, and Harlock Creative. All of the work that I'm going to present, some of it will be related to these companies, but any of the research that's done is done under a conflict of interest management plan approved by Northwestern, Shirley Ryan AbilityLab, and the NIH in DoD if applicable. So Shirley Ryan AbilityLab, we used to be, as Aaron said, the Rehabilitation Institute of Chicago. We changed organization in 2017 to the Shirley Ryan AbilityLab. This was for a variety of reasons, primarily being that we had outgrown our existing space, and it wasn't as a pleasing environment to do rehabilitation as we thought the patients deserved. So they took an initiative to make a new a new hospital. It's a 242-bed inpatient facility. It has private rooms, much larger footprint. The research portfolio, that's not annual, that's cumulative under contract, so it's $130 million, generally over 3 to 5 years. So our annual research budget would be something like $40 million. 43 principal investigators. It kind of hovers around there, maybe it's 45 now. We have lots of things to support the hospital. This is again, my marketing slide from the Shirley Ryan AbilityLab. This is our mission, is to advance human ability and to be the global source of science-driven breakthroughs in human ability. So moving into the Center for Bionic Medicine, we were founded in 2006 by Todd Kuiken. We're around 100 people these days, and we have about a $48 million US dollar research portfolio. So we have a significant portion of Shirley Ryan AbilityLab's research money flows through our center, either through partnerships with other labs in the AbilityLab or through our own grants. And we really promote the seamless integration of scientists, clinicians, engineers, students, operations people all working together. We definitely focus more on translational research than on basic science. And we're located here on the 11th floor, just above the main entrance. The first 9 floors are parking. And so we are a team more than just on paper. This would be a typical day in the lab. And what I want you to notice is that the focus is on the user in the middle of the center, right? So the user is talking with a therapist, and the therapist is communicating with the engineers and scientists, because we don't even necessarily speak the same languages, right? So the user might say, I want this to feel smoother, and the engineer might need to change the damping parameter of the controller. And so the therapist is kind of translating, it's like, does that damping parameter feel better? And the user's like, what the heck is that? And so they're basically like, does this feel smoother? Is this what you're asking? So we're a team, and more than just on paper. We are all working together to try to solve these issues. So there's myself, and I'm interested in control of upper and lower limb devices, as the things you'll hear about today, or some of them. Arun Jayaraman leads a large group. He's an established principal investigator. He'll do a lot of industry testing, wearable sensing, just a large group. Megan O'Brien is a newer principal investigator. She's looking at wearable sensing, community monitoring. And then James Cotton is a MD, PhD. He's looking at precision rehabilitation, biofeedback studies, markerless-based pose estimation. Again, he's a more junior PI, but he's really rapidly establishing his research program. So I said we're like around 100 people. This is how I think of our team being laid out. So we have our scientific leaders, who I just told you about. The academic team, these would be the students and postdocs and residents and team scientists. We have a technical team of professional engineers, right? So these would be roboticists, mechatronics engineers. They might have a mechie or EE background. Then we have the clinical team, who are physical therapists, occupational therapists, prosthetists, speech-language pathologists. They all kind of sit with us. And then our operational team, they kind of keep the center running. And these would be the areas that we would do well in, I think. And we don't do any of them in isolation. So machine learning and data science, mechatronics design and control, and clinical trial execution. And I'm going to be talking about components of all of these aspects of our work throughout the talk. So I'm going to first start off with upper limb prosthetics, tell how the center was established, move into lower limb prosthetics, some of our work controlling prosthetic legs, kind of at a legacy level using state machines, and then move into more deep learning, modern AI approaches and how we're applying them to some of these prosthetic legs to conclude the talk. But before I get into there, a couple of disclaimers. I'm going to show a few videos. Take them with a grain of salt. Like most researchers, I show the absolute best video that we've been able to collect in many circumstances, except when I'm showing how it dramatically fails. So we're kind of getting, I'll be honest and say this is a produced video. You'll be able to see them versus the ones that are more general in lab. So take everything I say with a grain of salt. And also I'm going to be talking about these cool bionic limbs, but this is kind of where we start from. This is a body-powered device, patent from 1912. It's still a very commonly prescribed upper limb prosthesis because it's lightweight, it's durable, it's functional, and it's pretty easy for the user to control. So when we talk about the innovations that we're doing, I always try to go back to what the baseline tech would be. So this has been available for many years, but it's not perfect. There's, of course, ways that this could be extended. This would be myoelectric. So again, for those that are unfamiliar, when your muscles contract, they generate a little bit of electrical signal, about 1/1000th of a volt. We can put electrodes on, sensors on the limb, amplify those signals, and then decode them. And the decoders that had been traditionally used were amplitude-based only. So whichever muscle was firing with a higher intensity, that would control the direction of the prosthesis. So if the flexor was firing more intensely than the extensor, the hand would close or the wrist might rotate. And to switch between the various degrees of freedom, you'd have to give a pulse, like a co-contraction, to signal that you want to do a different activity. So it's close, open, switch. Rotate the other direction, switch. That would be the way that this style of control is operationalized. Many years ago, people decided, they knew that you could use pattern recognition approaches. These are very simple machine learning approaches. So these would be statistical classifiers are generally what we've implemented. And so you look at the data from no longer a really specifically placed electrode. You can look at an array of sensors. You can extract some features from a short window of data and then classify that as belonging to any number of n classes. And you can kind of look at a mixture of the signal amplitudes to get an intensity at which you might move. So these mostly use velocity control. So you pick a movement, and then the EMG amplitude is mapped to the velocity that you want that movement to occur at. If it reaches the end stop, that velocity kind of gets transferred into a torque command. So we have commercialized this. This would be the COAP system on the upper left. These systems were really designed in response to more advanced, capable prosthetic hands. So the first multi-articulating hand came out in 2007. It was Touch Bionic's IRIM. Now these devices, there are at least 15 that I know of. You can buy them, you can fit them. Controlling them is not easy. So we kind of use this pattern recognition approach to seamlessly decode the movement and then tell the hand how to move using some sort of digital communication bus. It's a pain because all of these hands use different communication protocols and many of them use different physical interfaces. So being able to control all of these various pieces of hardware with wrists and elbows is actually quite challenging, and the machine learning component of it is probably a minor aspect of what we've traditionally done. This is 2012 when the system was first developed. He's using a trained decoder, only visual feedback, and he's just saying, I'm going to use seamless sequential control, so only one movement at a time, and he's able to guide these activities to feed himself, for example. So that's, again, this is a kind of a more realistic video back in 2012. It's certainly not the best video. And then this is what it looks like today, which you can see is a highly produced video, but you'll actually see some of the advanced capability, and you no longer have the lumpy socket. Everything has been miniaturized. Everything kind of runs in real time. There's no special extra battery. And users use these devices. We have a manual, of course, but they generally don't read the manual, and they'll just use the devices for whatever they want to do. And so these devices get sent at home. They need to be durable. The devices, the robots need to be durable. The control system needs to be robust just to allow activities of daily living. This is a hand only. You can imagine doing a wrist and an elbow in addition to that. So those all, that works well so long as you have muscle from which you can put the electrodes over, right? So most of the muscles that control your fingers and wrist are in your forearm, but if your amputation level is above at your elbow or above, you don't have the muscles in your forearm to put electrodes over. So it's kind of a myoelectric control paradox. And Todd Kuiken, who founded the center, and that's who hired me to go work in Chicago, he had developed a surgical technique to overcome this, and it really did change the way that surgeons and technologists and clinicians kind of work together, and it's become a model for many other groups to do successful kind of team-based science. But anyway, this is Jesse Sullivan. He lost both of his arms. He was a linesman. He touched both sides of the live wire. He had to have surgery for a pain-related reason. And so Dr. Kuiken said what he wanted to try was the pec muscle was still remaining and healthy, and the nerves that would have went out through the brachial plexus were still available and healthy. But they just weren't innervating anything. So he said, what I really want to do is segment the pec and then physically move the nerves that went through the brachial plexus onto the chest muscle, allow those nerves to grow into the chest muscle, reinnervate the muscle, and then put sensors over top of it, which will become clear in a moment. And he said, we can take those signals, use any sort of decoder that we want to control a prosthetic limb. This is what surgery looks like. I know it's lunchtime, but should have gave you a trigger warning. But the main nerves are, they look like little bundles of spaghetti. It's a nice, technically easy surgery. The surgeons can do that in, a couple of hours. And then after you reinnervate, you get these interesting patterns of activity. And so importantly, Jesse is only thinking about moving his elbow, moving it up or down, or moving his hand. He's not thinking about contracting his chest. You couldn't contract your chest like that if you tried. So it was an intuitive way to restore these neural signals, and we're not using the joint torque capability, generating capability of muscle. We're just using the electrical capability to decode, to pick up and decode. And this kind of had an immediate benefit using technology, the remaining technology at the time, right? So you could put this into commercially available elbows, wrists, and hands. This is a Greifer, right? It's a powered hook. This video was probably taken in 2003. But you could do this for above the elbow. You could reinnervate a segment of the biceps and a couple segments of the triceps with the median and ulnar nerve just as easily as you can reinnervate the pec with the musculocutaneous and the ulnar and median nerve. And so we had these dramatic improvements of control immediately after the reinnervation. Reinnervation, depending on how far the nerves need to grow, takes they'll start to reinnervate motor units in about a month, and then you have a good signal that you can measure in around, call it 4 to 6 months. You start having a pretty stable neural interface. And of course, you get reinnervation of all sorts of interesting patterns, right? So I showed a video of elbow up, elbow down, hand open, hand closed. You get reinnervation of intrinsic hand muscles as well. They're just all mixed together, right? So you have these big nerve bundles that get coapted onto the segment of the pec. It's kind of a little bit random which ones make it through the pruning process, but you do have contributions even from thumb muscles and finger muscles in the motor units that you're generating if you can measure them. So we've used high density electromyography in an attempt to decode these with various levels of success. It turns out that you basically can you can reliably control around 10 things, most people. Some can do 6, some can do 14. It's a bit like operating a crane, right? So some people are better equipment operators than others. Some people are better drivers than others. So there is some human learning capability that we don't fully understand who's going to become the best operator or why, and promote that. It's an interesting scientific question that people continue to work on. And we, of course, went through and did the reinnervation surgery. It's one thing to show a couple videos. We do these outcome measures that are kind of validated in the upper limb control literature. And we've done the reinnervation surgery at all levels, and we've did modern machine learning-based control, modern-ish machine learning-based control, and amplitude-based control. And generally, the results are exactly what you'd expect, which are transradial, so people with an amputee below their elbow are a little more functional than amputees that have their amputation above their elbow. And applying advanced machine learning improves outcomes a little bit more than just using the amplitude. So none of this was shocking, but we spent probably 8 years doing the clinical trials that essentially allow for that to give the evidence to justify reimbursement. And that surgery is now done probably 10,000 people, 5,000 to 10,000 people have had the TMR surgery. It's kind of a standard of care because it reduces pain in addition to having a better functional outcome. And then more recently, we're working on osseointegration. So with osseointegration, you put a titanium implant, and this is a partnership with Integrum and Max Ortiz-Catalan, who's now in Australia. But essentially, we want to put sensors inside of the body, and it's challenging to make sensors that go inside of the body that are wirelessly powered and stay on forever. But if you put an implant through the skin and attach it to the skeleton, people have been working on ways to make these implants stable over time. And so now you already have that portal into the body just hollow out the implant, feed a wire through, and then you can start wrapping nerve cuff electrodes around, put electrodes on different muscles, do reinnervation, do other surgical procedures that have since been developed called regenerative peripheral nerve interfaces, or AMIs, which were developed at University of Michigan and at MIT and Harvard, respectively. So we have this ongoing clinical trial, which is just getting started, but more to report soon. These are videos courtesy of Max. And then, of course, one of the main reasons, I'm just going to talk about this real briefly, is that one of the main reasons we use such stupid and silly machine learning approaches is that we don't have enough data from people using the devices at home to train real deep learning approaches. We're changing that in that now we're able to monitor the signals and the user's activities at home. We're putting it through a cloud-based system. And first off, we can provide better informed therapy when people come to visit. But what we're really doing is we're trying to take the data, have people play video games, serious video games, and then use that data that's being collected from the gameplay to train deep learning algorithms. So that's where we're going with this. I think that might be a good time to stop for 2 or 3 minutes and answer any questions about that upper limb related work, if there are any burning questions. So the question is, when the TMR surgery is known to reduce pain, is it phantom pain or some other type of pain? So the type of pain that it's definitively have evidence to support that it reduces is neuroma pain, which is a scar on the end of the nerve. There's some evidence that suggests if you do it early, then that neuroma pain won't consolidate centrally, and that can alleviate phantom limb pain too. So it seems like it's a strong preventative aspect for neuroma pain, nerve pain. And depending on the time at which TMR is performed, there's some evidence that it could prevent phantom limb pain. And in some people, phantom limb pain is resolved, in some people it's not. Yeah.
In the hands, so there was the couple of videos of the person doing the hand, and the robot hand would basically do the same thing but delayed.
Yeah.
And much slower.
Yeah.
So is that, like, can you explain how much of the delay and the speed is like a feature versus just an engineering challenge that has to be overcome?
So the delay needs to be less. So there are a couple of types of components that contribute to the delay. The first one is extracting the information from the signal itself. Like the longer you sample in the signal, the more accurate you can make a decision, the more reliable your prediction is. And then there's a delay that's basically how long it takes to process that signal from which you're extracting. The processing time should be like 10 milliseconds or less. And then the window at which you are extracting, depending on which algorithm you're using, how many electrodes you have, where they're placed, those are all trade-offs that need to go into the decision. But generally speaking, that needs to be less than 200 milliseconds. And so we have some ability to tune that. So if someone wants more functions, they're going to have to tolerate more delay. But we're working now on decoders with like kind of exponential smoothing factors so that that data from recent time points are weighted more, and it's definitely improving things. In that particular video, there also was the Bluetooth communication, which normally wouldn't be part of the prosthesis control, but it went to a stand, and we were doing some other things there.
So is the speed of the fingers like due to the delays entirely, or is it also like
No, the speed just was set for the video, just you know, to make the nice produced video. But they are speed limited, and they're definitely move much slower than I would move my hand. And yeah, without sensory feedback explicitly timed, we can't get fast movement. No. So it's on that order. It can be a little bit faster than that. There is some proportionality to it, but you're not getting nearly anthropomorphic speeds in these devices. Yeah.
so as we develop like these further prostheses, and we start to add more control systems in it. I read research that a lot of people like to use the simpler ones because they're very mentally taxing to use, right? Is there a more state-of-the-art control that's starting to bridge that simplicity gap from, let's say, like standard, just using the more physical stuff versus something like
There are shared control approaches where you're looking at like camera-based things that pre-shape the grass, for example, and you just have to release an open-close signal. And then there are some sensory feedback systems that allow for us to create better internal models, which make it a little bit more intuitive. Those are still under research investigation, but they're not clinically available. So I'm going to move on to the leg component, and we'll come back to additional arm questions if there are any later. But we got into legs because of the success that we'd had in doing clinical deployment of our upper limb work, and there was a larger population for individuals with major leg amputations. So depends on the person how well they're able to walk with these legs, but this is not an unusual video of someone walking with a prosthesis. They don't have normal biomechanics, although some people can walk pretty well with these devices. So I don't want to give the impression that these devices are terrible, but these are some examples of people learning to walk with devices and some mobility challenges that individuals would have. If you look at the best walker with one of these microprocessor legs, they are actually quite functional. We've been developing devices at the Shirley and AbilityLab and testing others, devices that others have made. So we've worked with Vanderbilt extensively in some of our early work from the Goldfarb devices. Worked with Elliott Rouse on the open source leg devices, some of the early devices. We've since moved on from those. And we're working on newer devices that we've been developed. A lot of the core development work was done by Tommaso Lenzi, who's now at the University of Utah. So we have lots of different devices that we're testing. And we've tested these from a lot of different people. So you're going to see, again, some videos and control approaches. Generally speaking, most of this type of research has been done with around 50 people. Some experiments are done with 10. Some experiments are done with 40. This is kind of the pool of users that we draw from for the specific experimenters, for the specific experiments. And mostly with a K level. K level means how well someone can walk. So it goes from 0, meaning that you can't walk, to 4, meaning that you would not notice someone had a mobility deficit if they were walking in this room with pants on, for example. And so we've done most of our work with K3 and K4, and increasingly amount with K2. And a K2 would be someone who walks maybe with a cane or a gait aid. That's mobile, limited community ambulator. And in spite of all of this variety of people, weights and heights and time since amputation, almost everyone has been successful in using these devices. So we don't use soft robots. We're using rigid devices. This is a video from Elliott Rouse he gave to me, and just showing the control capabilities of a device if you spend some time, what they're potentially capable of. I've never been able to get one of these open source legs to do this, but I'm not as smart as his graduate student, Hung Lee, I think, who did this one. We have been able to get them to behave like this, though. And so this would be the typical way that we have traditionally controlled these devices. So we model the joint as a mass spring damper system, and we're able to tune the parameter of the stiffness, the damping, and the equilibrium position of the virtual spring. We don't change the mass. And so we have these tunable parameters, which are the stiffness, damping, equilibrium position of the joint, and we are generally tuning a knee and an ankle. You notice, I think Aaron's in the background. I'm going to say he wasn't controlling the device. He was just recording the data. He might have been hitting a button to make it do this. But this is what we're trying to restore. We measure EMG signals from reinnervated leg muscles or naturally innervated leg muscles. And we're trying to predict the activity that the user is doing in real time before it occurs. And so we're trying to restore natural mobility for this type of walking. And I'll say this video, again, was probably taken in 2010-ish. And I'm sure that, I know that this actually is a real-time control system because it's using the EMG-based control in that aspect. What we've been spending most of our time on in the last 10 years is making this work every time someone puts it on without a team of people helping, right? So we know how we could do it. Whether it's the best way or not, I'm not going to say at this point. We know that it can do this. We know that it doesn't do it every time the person puts it on without any training. So those are the reliability, robustness, and then expansion of capabilities are really what we've been focusing on over the past 10 years. And again, the way that generally these devices are working, doesn't matter which device we have sensors related to load, position, velocity, kinematics from the knee and the ankle. We have inertial sensors, and sometimes we use EMG, although most times we are not using EMG just because it's such a difficult signal to use practically. It takes a long time to set up. So generally, we're doing many of our experiments without EMG. And so all of the legs, kind of from the different activities, these signals generate different patterns, and so we can use state machines or machine learning to create controllers to replicate these patterns. This would be an example of, almost all of our work up until maybe the last couple of years uses this style of control. So it's a hierarchical finite-state machine-based controller. The high level, we're predicting something on the order of 5 hertz, maybe 10 hertz these days. Mid-level control, these are essentially generating the trajectories. We do those something like 200 hertz, and then the low-level control, we're using like open loop current control or impedance control or something. We do those at a much higher frequency. And again, we model the knee and the ankle, torque at the knee, torque at the ankle, by the stiffness of the knee and the stiffness of the ankle, equilibrium positions, damping factors. We get the measurement of the speed and the measurement of the joint from the device. We generally are using hard thresholds or rules to transition between the activities. We subdivide these activities into subphases, and to change between the subphases of gait, like stance 1 to stance 2, we're looking at some rule, like the vertical, the IMU measurement through the vertical says it went through 0, and so I need to transition from a weight acceptance to a powered push-off. So we have good control parameters for the within mode or within activity controller. Changing between controllers has traditionally been more challenging, so if you want to transition from a walking to a stair, that has generally been more difficult to do. And again, basically when we started this, we were using a pretty simple approach, which is we had discrete events of the gait cycle, when the heel contacted the floor or when the toe came off, and we would look at information specific to that phase. We'd train some sort of pattern recognition. We've looked at neural networks. We've looked at support vector machines. We looked at statistical classifiers. They all do reasonably well just because of the way that we subdivided the gait phase. And then we also add in some temporal information associated with what you had been doing to build that in through a kind of a dynamic Bayes approach. And if you want more information on that, you can talk to Aaron. When we first started, we thought that the transition points were going to be critical. And the transition points we we'll say arbitrarily defined as at the bottom and the top of a ramp, the bottom and the top of stairs. And they are important transition points. However, it's more important to get every step right, independent of the transitions just happen to be events in walking, but any error at any time could potentially cause a problem. So we thought transitions would be especially important. I no longer believe that. I think all errors could be important depending on the situation, and transitions are one important part of gait, but they're certainly, I don't think any more or less important. In many ways, they're less important because when they're transitioning to go upstairs, for example, people are willing to stop and do something, versus when you're seamlessly walking and you have an interruption to your gait, that's more surprising. So changed my thinking on that a little bit. But right here, if it did not transition, you would kick the step. So you have to transition the controller to have a more flexed knee. And at the top of the stair, if you don't transition back to walking, the knee would hang up and not be in the correct position to bear weight. Similarly, going down the steps, if you don't transition at the appropriate time here, for example, and it's too stiff, you could jackknife over the device and then fall down the stairs. And at the bottom, similarly, if you're not ready to bear the weight, it's going to feel like feel soupy or sticky. And these are examples of what happens when those transitions go wrong. Sometimes people don't even notice it. So like the biomechanics of walking up a shallow ramp are similar to walking at a fast speed, and people rarely notice that perturbation. More frequently, people notice something, but it doesn't necessarily cause them to stumble or fall. Just something feels off. So like this is not working properly, but he's able to get through it. If he wasn't in a place that had handrails and a team around him, I'm not convinced that these wouldn't cause more problems, but generally speaking, they're not the big issue. But the ones that are the big issues are kind of on the stairs, which you'll see in a moment. And the other thing is one mistake leads to another mistake. And so if you have a device and it behaves like a belt slips, the next step is going to be totally different because the person no longer trusts the device. And you probably after time, they regain trust, but their walking patterns change almost immediately if something goes wrong with the controller or something goes wrong with the hardware. So again, these are older videos. You can see John Spanius and Nick Fye and Kim Ingram and Aaron, and everyone's they're one of the ones who actually developed this. It worked pretty well. And then so people don't just put this on and go, right? So you shouldn't underestimate the importance of having a little bit of clinical training if you wanted to deploy these into the community. So this is a physical therapist who is working with the patients to teach them how this device is going to respond and push back to the user, right? So we've taught people, we spend a lot of time teaching people to use these devices, especially before we send them home with one of these types of devices. And we've only sent a couple people home for a week or two at a time with these devices. More frequently, we're doing training protocols and then pre and post biomechanics type of work. But we have successfully sent a couple people home. So I want to revisit the state machine a little bit. I kind of glossed over it and made a nice pretty picture of what the state machine is. When the cartoon version I showed earlier, this is actually our user interface on our system, which we call CAPS. So this is only showing the kind of within mode transitions. This is kind of showing all of the other state machine transitions, many of which are just for safety. But you can see that it becomes unwieldy pretty quickly, right? So we have people who can configure these and make these and adjust the, 400 parameters associated with the impedance parameters and then the 600 parameters associated with the transition, but it's a problem. Essentially, what we're trying to do is we take these signals, we put them through our state machine, and we're generating impedance parameters, right? So we have an input, which are signals, and we have outputs, which are impedance parameters, and we have examples from about 50 people. And from those impedance parameters, we're generating current commands to the motors, right? So this is breaking down what our actual task is. This is ideally set up to be replaced by a network, right? And we used a neural network, deep learning based approach. This is work by Min-Jae Kim. And I wouldn't say that there's nothing specifically clever about this network. We tried a number of different topologies. This is a LSTM layer and a convolutional input, and it's a modern architecture, but there's nothing, we didn't invent a new transformer or anything. We just took things that were in the literature and assembled them, and we put it on, and lo and behold, it actually worked pretty well, right? So this is a user that's no longer walking on a finite state machine. He's just walking, the sensors are being input into the network, and he's kind of walking along, and the knee and the ankle impedance parameters are being predicted, and then we're using our same impedance law to predict the joint motor currents to the motor. And you'll see in a moment, I think he might go upstairs, although we'll see. Maybe we didn't get stairs on this. I think we did. I want to make sure my video just isn't looping. Yeah. Again, so it's the same deep network as predicting walking, ramps, stairs, and that's good. We give ourselves a pat on the back, but essentially all we've done is learned our state machine, right? So we imposed a control law and had people walk on it, and now we're able to learn that finite state machine as you should. So what? Anyone should be able to do this, and anyone can if you have the data. So we said, it would be much more powerful if we didn't actually have to collect data from people wearing a prosthesis, and we could just take data from the literature, which is collected here. When we fused this with a few other data sets collected at other locations, like Bobby Gregg did some in Texas. And we said, okay, we have sensors that we have access to generally on the prosthesis. Like you have an IMU, we have an IMU. You have EMG, we have EMG. You have goniometers that measure joint position. We have motor encoders. Let's fuse all of this information and see if we can no longer rely on our state machine and no longer rely on our example sensors and train a network that way. And lo and behold, that worked too. So without getting into the details, Min-Jae Kim wrote a paper on this. And again, it's a slightly different network topology, but again, nothing, this isn't a new type of model. It's just an assembly of existing approaches with some clever domain adaptation to make sure that your sensor is in the same space and scaled the same, and just some standard signal processing. And again, we're able to predict impedance parameters, and in fact, we can predict joint torques as well. However, I don't think that the people, when they actually try this in real time, they preferred walking with the predicted impedance parameters rather than joint torques because of the bandwidth of the oscillations that were provided. So they preferred walking on the controller that did impedance parameters. So we're also working now with osseointegration. I have 2 more slides and then some time for questions. But one of the big problems associated with measuring EMG or including EMG signals from legs is that practically collecting those EMG signals is very difficult. You have to put sensors inside of a socket through which the person is bearing weight. And if they move or piston, they can cause a blister, they can pull away. There's all sorts of practical challenges. If someone has osseointegration, again, so this would be a titanium implanted into the femur, even without having the implanted electrodes, which we hope to get eventually, we can put surface EMG through a textile, like a cuff or adhesive electrodes in this specific example, but you could do it easily with a cuff as well. And now we have start generating these kind of, I'd call them lab quality EMG signals versus something in a socket looks pretty terrible. It's good, it's what we've been able to do, but from an EMG understanding the contribution of individual muscles is very difficult to say, we think we're measuring from the muscle we think we're measuring from and using it in any sort of biomechanically appropriate way. And of course, we're able to do not just non-weight bearing, but weight bearing as well. And so we actually took one of these, we took 3 open source legs to Sweden in hopes that one of them might work on any given time. and collected data over 2 days. And this is Max Ortiz-Catalan's old lab. And we're now actively recruiting for people with osseointegration in Chicago to extend this work. So with that, I think we have some time for some questions, and thanks for your attention, and I'll try to answer anything that I can. Dr. Sweet.
Great talk, Levi. I'm interested in the learning, like the team of 4 people you showed at the beginning, right at the outset, right?
Yep.
Are there formal ways to improve that process? Like
So
through video capture and behavioral science, etc. I wonder if there's ways to improve the tuning in terms of how the team interacts. Is that going to be replaced by AI agents?
So if you talk to Jose Pons and others, even I've heard here today, yes, it's possible that those interactions could be supplemented. I would never want to say replaced, but supplemented, made more efficient through some language models, for example, or AI agents. We are working with implementation scientists, and so implementation scientists, they try to sort out if you have a new approach or a new widget and you're trying to get clinical adoption, they'll go through an evaluation of the process by which you introduce it to a new population or clinic and provide feedback on what you perceive to be the pain points, what they perceive to be the pain points, and optimization. So we do work with Miriam Rafferty, who is an implementation scientist. Not on this yet. It was a little bit early. It's probably ready for that now, but that early development was probably, she probably could have told us all the things that we needed to fix, and we would have said, yeah, that makes sense. But now, I think she would provide feedback that would be beneficial. Yeah.
Quick follow-up, are there key things that you've noted that always occur in that process? Like early on, the engineer is important, and later on, the clinician is important in the learning process, for example?
So we've learned that being able to have the person independently don the device is a real empowering factor that allows them to trust the device more. So if we have 3 or 4 people that are helping them don it, turn it on, say, don't do this, do that, wait, the more instruction we have, it's kind of a gadget tolerance, the more instruction we have to provide, the less, the longer it takes for them to become proficient. If you can just hand the device to them and say, put it on, would you like help, rather than let me put this on for you, those things really, really make a difference in more of the clinical side of it, rather than if you're just measuring biomechanics, maybe not, but when you're trying to teach people to do, to take it outside on the street of Chicago, that stuff is a big difference. Yeah.
I was wondering if you could speak a little, you were kind of hinting at the end of doing some invasive EMG work and the difficulties with doing surface EMG. So when it comes to kind of looking at the utility of mechanical sensors versus bioelectric sensors, do you think that having the invasive EMG is kind of going to dwarf the importance of mechanical sensors if you can get direct invasive signals? Or I guess how much of EMG being and providing utility do you think is being held back right now because it's surface rather than invasive?
So I think the practical issues associated with EMG have limited the field from making decoders that are clinically and commercially available. I think there's benefit to be added through EMG in combination with some of these surgical techniques. So, for example, if we could restore through TMR, plantar flexion, dorsiflexion commands, I think we could modulate the amount of push-off we get. And I think users might like that, but we have not been able to, that's a hypothesis at this point, right? We haven't tested it. However, if you look at some of the work that Dan Ferris and others have done, where you give people proportional myoelectric control of ankles, there's some evidence to say people will use it. And, we don't know. I think that there is a small benefit to be added by EMG, but it's to be determined if that's like a clinically important difference or not. we will, but I don't think existing outcome measures are going to capture the benefit that's provided. We're going to have to come up with some sort of new way to quantify the improvement. Like, I don't think the amputee mobility predictor is going to quantify that. And metabolic, maybe, but I wouldn't want to rely on that as being the quantification, although it might get it. So I don't know. I'm not willing to give up on EMG. I'm just waiting for someone to solve the problem of the practical implementation. And we've been tired of waiting. We're actually going to do it. We're working on, I wouldn't say we're going to be successful. We are trying to do it. Yeah. But we waited a long time and there wasn't a solution. So now, in addition to doing the robotic hardware, we're going to do a neural interface too.
A lot of the tasks that you showed, I would call more steady-state tasks. So like steady-state overground walking, even stairs, you sort of get to a steady-state point. And you mentioned trying to go out into the real world, especially in Chicago, where the sidewalks are terrible, you have ice, you have snow. I guess what do you see as the grand challenges to be able to actually implement a device in those real-world settings? You're going to get step-by-step perturbations, you're going to run into people, stuff like that.
Yeah, so you're right. A lot of the videos I show were steady-state tasks. The way that we configure these devices now are we have pre-trained models from the group of people we have. We put it on, we lock it into a mode like walking, and then we just immediately try to trick it, right? We have them do varied walking, varied step length, turns, cuts, and we see what, if any, data would cause an error to occur in our control system. And when we first started doing this, this would be 3 minutes, 30 seconds. We would get data that would trick the control system. Now we're up to working with the device, say, for 45 minutes before we get a situation in, I won't say out on the sidewalk or on a bridge of Chicago where the bridge is going up and down and a bus drives by, but we're getting to build, and we're understanding what causes the system to fail much better. And I think you could supplement the approach with biomechanical modeling to generate more realistic data that we have not been able to capture. So we're going to rely on the biomechanical modeling community to help us in some sense. But again, it's a great point. I don't know the answer. I know that our control, for me sending this home, in no way does the control system the limiting factor for sending these devices home. It's the robot at this point. And we are willing, we don't want to cause a fall, but if people fall while wearing the devices, people fall while wearing an existing prosthesis. We don't want to be the cause of a fall, but we understand that it's possible that people while wearing our devices are going to fall.
So you touched on this a little bit about having people take the device home and use it for some limited time. How have you seen the individual's behaviors change from like a week to maybe longer? Do their gait patterns change with and without the prosthesis? And same question for the upper limb, which seems more like a motor learning task if you're relearning these muscle behaviors as opposed to the lower limb.
So we have a lot of data on the upper limb. So basically they learn the control system pretty quick, on the order of a day, hours and day. And then they learn to use the control system in combination with the device over weeks and months. So there'll be this rapid improvement over the course of a day or two, and then a slow evolution in control when they come back in 4 weeks later. They've learned how to use the control system and its limitations to do these outcome tasks much quicker. Like they know how to pour a box of cereal or whatever. When you first expose them to this control system, they might have to figure that out. So after about a month or so, we see improvements, and we bring them after like 6 months, and we see some additional improvements, but not nearly as much as that early time point. So probably on the order of weeks for the upper limb. For the lower limb, the people that we've sent home have been like extremely well trained. They participated in all of our work. They would be our star walkers. So the better example I can provide is the K2, so low functioning individuals. We're putting them through like an 8-week training protocol, and we see huge differences between week 1 and week 8 as they're working with the therapist to use the device. So I don't know. We know that they have a lot of learning and improvements, but I don't know at home how much I just don't know.
I had of the
I don't know. I think a lot of it is, a lot of these people just have not been trained well anyway to use a prosthesis, so they get some benefit just from working with a PT for 8 weeks. And then they get some benefit in learning to trust the device more, and then they probably get some benefits in the actual device providing benefit, right? Everyone says that they like the stability that it provides going down ramps and going downstairs. Because that's something that a microprocessor does not, like, it can provide damping, but it can't hold you up. You know, it's velocity dependent resistance. So these motorized devices can provide a hard stop if we want it to. And so I don't know the answer. They're definitely getting most of the benefit, probably just from 8 weeks of PT. Probably. But we'll have to test that. And we have protocols in place now to test that. Mm-hmm. No, that's like from control theory. If you put a delay in, people just oscillate around. Like if they're trying to reach something and it's too much delayed, they'll just overshoot. And they, you know, that's the primary cause of it. If it's too short and it's unreliable, then they get frustrated and won't wear the device. So it kind of, the shorter the better. Like if we could make 1 or 2 or 5 milliseconds, we would. We just, our group doesn't know how to do that, and I don't know if anyone in the field does yet either. But the longer part of the delay is they'll just oscillate around the motor point, and eventually they'll figure out how to the output of the command. Eventually they'll figure out how to do the best they can, but it's frustrating to position something. They have to kind of generate a ballistic movement and learn that model, and then wait for it to happen. And they get pretty good at doing that, don't get me wrong, but it's challenging. With sensory feedback, they'll get a lot better at that, in my opinion, or, you know, that's my guess. They'll learn that model much quicker. That's what computational motor control theorists would have told me. So it's not my idea.
discrete classification related to like moving our arms or like wrist or like hand movement.
Mm-hmm.
So I was wondering if some continuous control is possible, not just a discrete classification. And like, is there research going on with that? Are there like clinical applications?
There are a lot of people working on continuous decoders, control using like a regression-based approach. Everyone puts a hard threshold in because at the low levels it moves around too much. So even though they're working on continuous control, they are still artificially imposing a hard threshold at low levels. And I think that neuromuscular-based control and continuous control approaches are definitely worth pursuing. They will get better with implanted sensors, I think. And I think that that's, you know, I think you'll see benefits from those, but it's not going to be as easy. There are a lot of tricks involved to make this work for people at home. And so I don't think those have been overcome with continuous controllers yet. The tricks being like thresholds, like if it's moving at a low level, just make the prosthesis not move. We need vastly more amounts of data. Yeah, but I think it's a good area to investigate.
You mentioned that the users for your lower limb devices preferred the predicted field parameters over the biological board. Is that for one device? It looked like the video was the OSL, or across all devices?
We've only tested that control system with the OSL. And so I suspect it's going to be across all devices. I suspect it's going to be even worse with some of our devices that have better bandwidth. But I don't know. But yeah, I think it's if our estimate was better, I think that in the long term they might like it better. But our estimate is still too noisy that the impedance just filters out the noise. So more work to be done. Like we're just really getting started on that, and we haven't done as much work as as we plan to, or others will do, I hope. So, but I think fundamentally the approach is sound. I think it'll work.
I'm curious where insurance comes with all of these considerations in research. Like, do you think about insurance considerations as you're doing the scientific research?
I think of insurance considerations every day, especially through my role as a startup company too. So all of these these devices are, the cost of the device is not the driving cost of the care, right? So let's say the device costs 20 grand, probably would cost 40 grand if you're getting it from a prosthetist. And they're probably going to bill 250,000 to the insurance company. But you get the fitting, you get the training, you get the rehabilitation, you get a 5-year warranty, you get all of that associated with the final bill. So the insurance company wants to know the clinical benefit of this. And so for the upper limb work that's been available now for 10 years, and they still call it experimental, even though we have lots of data showing that it's, it's not as good as my hand, but it's certainly better than the alternative. And so that cost just needs to be covered. So from a research perspective, you should think about, if you care about the insurance side of it, you should just think about framing the research in a healthcare economics way rather than a hypothesis-driven way. And both have tremendous value, right? So I wouldn't not do a hypothesis-driven study because I care about insurance, but I would be careful in what I claim. Like, people say prostheses are abandoned because of control systems. That's not true. Prostheses are abandoned because of a lot of reasons, one of which is control system, and only for a subset of population. So the way that you frame your research is important. So I'm going to make a machine learning approach and test it on 5 people without an amputation, and your motivation of your paper is that people abandon prostheses. That's not good. So don't do that. But if you say, I have a new scientific approach that could potentially improve control and do an experiment, do that. So just the way that you communicate your results is important. All of this stuff will be insurance reimbursed at some point. Yeah.
I guess building on that question too, in terms of insurance, you mentioned that PT, just getting PT was a big reason why you think the users are improving so much over that HT period, where at the AbilityLab you have access to the best PTs in the country. So how do you think you can transition that model to other places if we are going to implement this, where you need sort of these PTs that are highly trained and just more PTs in general?
I wish I knew the answer. We're going to have to show evidence that the PT is a critical factor in the improvement. Like, that's the first step, is to show that PT is a required component in order to get these outcomes. And then we have to solve the problem of training the PTs and then access. But we recruit mostly we recruit broadly across the Chicagoland area. So some of these people have come through Shirley Ryan, some of them haven't. And some of them had their limb prescribed to them 15 years ago, and they just, need routine PT. Probably monitoring on the device will give some clue as to when you need PT from an evidence-based backing. But, I don't know. But the first, showing that it's important is the first step, rather than me saying it's important. I think it's important. We'll have to prove it.
Is there a way to shift opinions on what outcomes matter in the insurance conversation? For example, how valuable is preference?
So that work is happening now, and the Limb Loss Preservation Registry is trying to consolidate outcomes from at a national level to change that conversation. So they want it kind of at a national level, what matters to people. And the whole system is probably going to move to a what I did type of billing to what it did for me type of billing. And I think once that happens, then this conversation is going to be totally different. Right now, you get paid for what you did, not for what it did for you. And once that happens, I think all of these outcomes are going to be changed the way that we think about them and insurance companies think about them. Thank you. I appreciate the questions.